the men. Right? He's looking at not the choice. What he just said has to do not with what I'm doing as a picking somebody. He's looking at the class structure. He's saying, here's your space of choices, or sometimes we call those outputs, or possibilities. And you have 40 women in the class, right? And you have 70 men. What he just said does not describe anything about what does it mean. What is this? How much is this? Is it really 0.37? I'm not sure. 36. Fine. He didn't say anything about 0.36. He didn't answer my question. He just talked about how the possibilities look like. He was saying, okay, here's what your class looks like. You have 40 women, you have 70 men, and you can choose one of those, right? Right. But the question was, what is this 0.36 meaning? What is it really? 0.36 of what? Or how do I look at this 0.36? All set? Very good, thanks. We didn't lose the camera. That's a good thing. That's an expensive camera, right? We don't want to lose it. Okay, so what is this 0.36 in English, please? I mean the math. How can I think of some sort of thing that if I do that, I get 0.36?
If you think of all the possible outcomes, the 0.36 is the percent of those outcomes that are desirable.
Okay, so you replace odds with percent.
Oh,
so it's chance, risk, likelihood, odds, percent, right? Probability. What else can we fit in there as a synonym? Proportion, right? Luck, right? What's your luck to be picked to clean the board? 36, right? Fine. So there's many synonyms that we can fit in there. Great, and you guys know those. I'm asking, what does actually mean? Percentage, proportion, luck, odds. What is that?
If you pick 100 people, about 30 times.
About 30. If I pick 100 people, you say?
Yeah.
Or out of 100 people?
If you pick someone 100 times, about 36 times.
So if I pick, you mean, let's see what you mean by pick 100 times. I like this one. This one does not include the name, odds, chance, percentage, luck, or something like that. It's saying what? If I am to do this, pick somebody to clean the board, every lecture, right? That's what you mean 100 times. From now till the end of time, I decided I'm going to be a badass teacher and I'm going to pick a student every lecture until I retire, right? 25 years from now, every lecture I teach, I'm going to pick somebody to clean the board. What you're saying, the 0.36 then is what?
Is the number of times you would pick a woman.
Not the number of times I pick a woman, but you're close. So I'm always picking somebody from this set. But I'm doing it not just 100 times, I'm doing it from now till retirement. I'm probably going to teach 3,000 more lectures by then, right? What is 0.36?
The percent of times that it gets close to picking.
If I do this 3,000 times, and I count all these 3,000 times, how many times I got a woman, that number of times divided by 3,000 should be roughly this, right? So what's the answer of that question? If I repeat, pick 3,000 times, and I count the W's, how many times I got a woman, right? I should have what this 0.36 in count divided by 3,000 should be approximately 36. The reason this is different than saying odds or luck or chance, it's actually corresponding to a physical experiment. I could do that, right? I could, from the next 3,000 lectures, pick a person to help me with the board. I could count how many times I've seen W's and how many times I've seen men. Like how many times I pick a woman, how many times I pick a man. I can do that count and I can divide by how many times I run that experiment. And when I do that division, what this is saying, is it saying it's exactly that? Saying that if you do this, you're going to get exactly 0.36? No. What is it saying?
It's closer and closer.
You should get 0.36. Mathematically, what's saying closer and closer? How do we say that mathematically? Closer and closer. Tends means when? What does it tend?
When the total number of outcomes tends to infinity. So
Let's say that again. So what does it mean, this 0.36? It's not like if I do this 3,000 times, the count of, this is the count of W, right? Should be exactly 0.36. But what if I do it 6,000 times? What if I do it 100,000 times? What if I do it 1,000,000 times? Or 1,000,000,000 times? The more I do it, the more this has to be close to 0.36, right? We say that's a limit in calculus, right? I can't say it's going to be 0.36 if I do it 3,000 times. And I can't say if I do it 6,000 times, or 8,000 times, or 100,000 times. But if as I do it more and more and more, that goes to infinity. We're talking about billions and trillions. This is guaranteed to become 0.36. It cannot go to a different number. This limit, if you'd like, it has to be 0.36. This tendency, right? So if I only do it once, suppose I do this experiment right now, I pick somebody to help me, what will be this fraction? The count of women divided by the size of the experiment. If I pick a woman, what this ratio would be? Again, I don't do it 3,000 times, I do it once. If I pick a woman, what is this ratio going to be? 1. What if I pick a man? 0. So if I do it once, my estimate, if you like, or my ratio will be either 1 or 0. So if this is n, so what about if I do it, so if I do it 1, if I pick a man or women, what my estimate is? This would be 1 out of 1 if I pick a woman, right? And it will be 0 out of 1 if I pick a man. What if I do it twice? There are several possibilities now. I can pick 2 women. If I pick 2 women, I believe that this is a 1, right? 2 out of 2. So for n equal 2, I could get either 2 out of 2, I can get 1 out of 2, or another 1 out of 2, depending on how I run this experiment, or 0 out of 2. This corresponds to picking 2 women. This is women, men. This is men, women, and this is man, man. Those are the possible outcomes, right? I can, again, I'm picking a person today and another person next Tuesday in class to clean my, the outcomes are women, women, that could happen. Or I could pick now a woman and Tuesday a man. Or I can pick now a man and Tuesday a woman. Or I can pick now a man and Tuesday a man. That's the possible outcomes. And if I look at these ratios now, if I pick 2 women and I do the division was 2 out of 2. If I pick a woman and a man, that was 1 out of 2. If I pick a man and a woman, that was 1 out of 2. If I pick 2 men, that would be 0 out of 2. So those kind of counts, as you keep doing it more and more and more, a percent of time, so to speak, you've got to end up to 0.36 eventually. Okay? So how we do this more formal? That's kind of an intro into what we're going to do. There's a lot of counting in there because you can see right here, the fact that I divide with some sort of total, it's the easy part. These 2 at the bottom won't be a problem, or the size of the space. The real problem would be counting the numerator. How many times you get a 1, right? The probability of seeing 1 in here is this case where I get a 1, and this case where I get a 1. It's not a 2. 2 is the same everywhere. It's counting the numerators properly, which is back to counting what we've done for the last 3 weeks. So let's do this more formally. There is say a die roll. What is So that's called a random experiment. The random experiment in this case was what? What was the physical model for how to obtain this? Was picking a student to clean the board. So in here, the random experiment is pick a student to clean the board. In here, what is the random experiment? Die roll. What physically, in the physical world, I have to do to simulate this or to run this? If I have a die and I have, what are the space of outputs? Let's roll them like that. When you roll a die, you can get 1, 2, 4, 6, 5, 3. There's 6 possible outputs, right? So random experiments, it's actually roll the die. This die roll is the name, but in a physical world, if we want to actually run this experiment, we have to pick a physical die and roll it. You guys know how die looks like, right? There's 6 faces. And what is a fair die? When do we call a die fair? What does that mean? If I say I have a die and it's fair.
There's an equal chance of it landing on, as you say.
Equal chance to land on any face. That's what we want in a game when people have those dice. Some games play with 2 dice, right? We don't want to have more likely to get a 4 than a 1. In games, a lot of games rely on the fact that all faces of the die are equally likely to come up, right? So then, the outcomes, of course, of rolling a die is one of these things. If I say equal chance, that means each face has what chance? If there's 6 faces and all of them are equal,
1 by 6.
it's 1 by 6, right? So a fair die, in probabilities, it has a name, it's called uniform. In games, when we play a game, we call it fair, but in terms of probabilities, we call it uniform. Equal, every face has a chance. Now, this is called an outcome, or outputs. Outcome of what? Outcome of my experiment, right? My experiment is roll the die, it produces an outcome. Now I'm going to define another thing. This space, let's call it, I don't know, it's called S, I think. What is this S, the space of outputs mathematically? What I just draw here. I call it space of outputs, but mathematically is what? Set. We like to call it probability space, but we really mean a set of possibilities. Now I'm going to define another thing, an event. An event, E, is a subset of S. For example, I'm going to define event E1 is even outcome. What subset is even outcome? If this is my entire probability space, that's the possibilities to roll the die, which ones correspond to the event even outcome? What outcomes are even? 2, 4, and 6. Right? I'm going to define another event, at least 3. What subset of outcomes that is? 3, 4, 5, 6. So people have this question, if you roll a die, what is the chance to get at least 3? What is the chance to get even? What is the chance to, I don't know, crash the die? All kinds of things. Those are all events. And out of the set of outcome, you have to say, okay, what is event E1? Event E1 is this one. What is event E2? Event E2 is this one. This is not different than sets, right? I mean, we call it different names, but we have two subsets, right? They have an intersection, right? There is obviously something that's E1 intersect with E2, which I could call it in English what? What would be the intersection in English? Even and at least 3, right? And as a set, if I intersect them, what is even and at least 3? 4 and 6, right? Which, no surprise, corresponds to exactly the intersection 4 and 6. So far, so good. Now, what we want is to define the notion of probabilities. Is a function in a general sense. Now, when you learn more mathematics, this kind of function is called measure. Not all functions are measures, but you don't have to worry about that, because we're not going to get to that level of mathematics to know which functions are measures. But you can just call it a function, right? So this probability, we're going to call it P. P can be defined on an event. So this function goes from the subset, right? P is defined on all the subsets, because events are subsets. So it's associating itself with every event. And the values of these functions are real numbers from 0 to 1. So P of an event, if the event has size 1, that is, say the event is, it's only one thing, right? Some one object. That is the probability of that exact outcome. In here, what is an event of that size only? Who's this in this probability? Remember this experiment? I was picking a student to clean the board. What is this circle? What are the dots, the pluses and circles in this experiment here? Students cleaning the board. What is each sign? Who was this? What were those? Yes.
All elements of the space of outputs.
Right, but in this particular case, what was the space of outputs? This experiment. Not the number. These are the actual students. That's Ryan right here. That's you right here. Right? Those are the actual students. So what is the probability of picking this student? That's an outcome. Right? So if this is Ryan, if you don't mind, I put your name on it. Probability of Ryan was what? What is the probability of one outcome picking Ryan? In this case, I do it uniformly. What was it? It's 1 out of 110. In here, if I have a fair die that is uniform, what is the probability of an event that has exactly one element? So we can write that as formally as a subset. I pick the 5 in here. But you know, nobody does it. Most people say probability of outcome equal 5. That's okay. Informally, we say that's a fixed outcome, one of the cases. So what is the probability of that 5? If the die is uniform. How much is it? 1/6. The probability of any outcome is 1/6 in here because it's a uniform outcome. Same thing like in there. The probability of any student, it's 1/110 because it's a uniform draw. Right? But probability of subsets follow the subsets rules. If I have two events, so if I have an event, in my case, event 1 was 2, what was this? 2, 4, and 6. I could define the probability of the whole event, not just one outcome, but that event. This is going to be probability of seeing the 2 plus the probability of seeing the 4 plus the probability of seeing the 6. I'm abusing the notation. When I say P of 5, you have to read that in context. That is the probability that the outcome is exactly 5. You shouldn't write this. I think you lose points if you write this in the homework. But you know, I don't get graded, so I can. No, it's kidding. You know, you have to be clear on what you mean when you write stuff. We accept informal things if it's clear what you mean. This P of 5 means the outcome is a 5. That's the event that formally is a subset of 5. And here, P of E1, that's actually P of the subset 2 or 4 of 6. Right? That's E1. And what is that? Well, that's adding up the probability of the members. So you can say add probability of members. How about probability? So how much is that, by the way? If I add up the probability of these 3 guys, how much is each one of them? 1/6, because my die is uniform. So how much is all that? 1/6 plus 1/6 plus 1/6. That is 3/6. How about the probability of E2? That is the probability. Now E2 is a different one. Is the probability of 3 plus the probability of 4 plus the probability of 5 plus the probability of 6. Formally though, this is really the probability of outcome equal 3. That's what it is. I'm just writing it fast, probability of 3. That again has to be clear from context what I mean. How much is this? By the same, you know, if it's 3, 4 objects, each one of them has a probability of 1/6. How much is it? 4 by 6, right? How many people with me so far? Any questions? This is probably something you already know and you have seen it. It's just written and talked on more formally. I think some of you already have this notion on if I pick 1 out of 110, there's 40% chance to get a woman and a 70% chance to get a man. And if I think of here's the probability of picking an even one, that would be about half because half of them are even. And how many of them are at least 3? It's 4. So the chance of that is 4 out of 6. It's just a little bit more formal. I want to continue this formalism with sets. I can define other sets like intersection or union. I could also define union is what? Even or at least 3. So what is even or at least 3? The union. That would be 2, 3, 4, 5, and 6, right? In this case. That's the same as with sets before, what we've done in the past. So what if I want the probability of the intersection event? That is these 4 and 6, right? If I know the intersection, that is probability of getting 4 and 6, which is either one of them. So that will be 2 divided by 6. Because it's 2 out of 6, they're uniform. How about the probability of a union? That would be the probability of the union. 2, 3, 4, 5, and 6. How much is that? 5 over 6. Very good. How about I say, I think in general, probability of a union is the probability of the first one plus the probability of the second one minus the probability of the intersection. Is that true? How about in this case? How much is P of E1? 3. How much is P of E2? Let's see if that's true. This is 3 out of 6 plus 4 out of 6, right? Those two that I completed here. Minus how much was the intersection? 2 out of 6. Is that really 5 out of 6? Do you think that works in general? This rule here. Sounds very familiar, right? It's the same rule that we had before, just with different names on it. Before, instead of P, what was our measure or metric? Was not P, was what?
Size.
The size. Now it's P. The size, it's like a probability, but definitely assign 1 to everyone. Size is a measure too, but the size always assign 1 for every object in the set. So the size of an object with 4 things will always be 4. The probability is not fixed like the size. In this case, it's equivalent to size because my die is uniform, right? Everyone gets a size of 1 over 6. So then everything is just like the size. But this works even if probabilities are not uniform. Suppose now I have an unfair die, the kind of die that people put a little metal in it, so 6 is more likely. Where do I have to put a metal so 6 becomes more likely? On the opposite side, make it more heavy. When you roll it on the table, the heavy one is more likely to come up at the bottom, right? Because that's the rule of gravity. So if I put the metal on the one side, I'm more likely to see the 6 on the top. That's how people cheat on dice. Now that die is not fair. It has more chance to look at the 6 and less chance to have a 1. So the event probabilities, they follow the same rules, but the event of each outcome is not 1/6. So if I have different outcomes, I still have these equations here. I can sum up the outcomes for the members of the event, but they won't sum up to necessarily 3 over 6 because those are not 1/6 each. But the rule still stands. This rule is still correct. As a metric, the union is the sum of the 2 events minus the intersection. And of course, before when we talked about sets, we said a particular case of this rule is what? That's an inclusion-exclusion, but there was a particular case that we call the partition or the sum rule. What case was that? When can we transform the inclusion-exclusion? Simply in summing up the events. What was the condition for partition rule to work? There's no intersection. Which is to say, in here, how would that look? If there's no intersection, I have the property of a union, is the probability of either that or that. There's no intersection, and this whole thing, P of the intersection, which is empty set, will become 0. So that's something that we need. We need to say that this metric has the probability that when you apply it to the empty set, it gives you 0. And when you apply it to the whole set, S, which is the whole space, if I want the probability of the whole space, I get, what is the sum of probabilities of everybody in the set? 1. So this is what makes it a measure. If you apply it to the empty set, you get 0. If you apply it to the whole set, you get 1. But remember, the difference between this P that we have now and the sizes that we had before. Sizes are guaranteed to simply be how many things you have in the set. P's are not guaranteed to be that. P's you can define whatever you want. If you play with this die, add metal to it, you can get the 6 to be a very likely phase, maybe 70% chance, while the 1 to be a very unlikely phase, 4% chance. So now my P's are very ununiform. Same thing in here, maybe I have a bias. Maybe when I pick, I prefer to pick beautiful girls, right? Now not everybody is equally likely. I would be a very mean professor to do that, right? I shouldn't do that, right? I could get fired for doing that. But nevertheless, some people do it anyway. So what does it mean? They do not have a uniform probability of picking students. Or maybe I have a different bias. I really like tall guys. I could have a reason for that that's legit. Maybe the board is so high that you really need a tall person to clean it. That seems legit, right? Is that probability going to be uniform? No, because the tall guys will have a much bigger chance of being picked than the shorter guys. Many things in reality, in nature, are not uniform. Nature has a tendency of not creating uniform objects and not creating uniform patterns. Our brains do not naturally think of uniform things. Even if you think you pick things at random, when you say, I could go to 3 movies, right, with my friends. Let's pick one at random. Have you ever said that? There's 3 movies, I don't care to which one we go. The truth is you never actually pick at random, right? You have a bias. Even though you said, I'm happy to go to any movie you like, you're not, right? You like some movie better than others, right? Come to any recitation you like. You're not going to pick one at random. You're going to pick one that you like, right? You can have any job you want, pick one at random. You're going to pick a job not at random. Pick a chair in the room. Any chair is equally good. Why you always sit in that spot? Then why you just pick one at random? How many times you sit in this chair? Why don't you pick one at random if they're all equal? We tend to not pick things at random, even when it's required by the law. Like I'm not supposed to pick a beautiful girl. It's actually a standard by the university. It's called discrimination, right? Yet most people have a bias. The bias is built in our nature. Even though we make laws against it, sometimes, you should expect in many situations in practice to not have a uniform probability. That's nice for mathematics, uniform probabilities, but in reality, things are never uniform. When it's likely to rain, it's not uniformly likely to rain over the year. Some days, some months are more likely to rain. What plants are likely to grow bigger? It's not a uniform thing. Some plants are likely to grow much bigger than others. Okay? So we've done this first example. How about I have 2 of those? Different experiment. 2 dice. Pair. Both of them. What's my experiment? Roll both independent. Independent, I mean, I roll them without paying attention to the first roll or second roll. I roll them with one hand, the other hand, simultaneously, and I read the outcome. What are the possible outcomes? If I roll 2 dice, here's the first die. 1, 2, 3, 4, 5, 6. This is the first die. It can come either 1 or 2 or 3 or 4 or 5 or 6. So that's die 1. And here's die 2. It can come as 1, 2, 3, 4, 5, and 6, right? That's the possible, that's the second die, right, 2. The outcomes are the pairs that I observe, right? What's an outcome in here? A pair of values. And suppose I treat this outcome out of order. Meaning I don't know which die is which. I roll them both on the table and I don't know that one die is red and the other one is blue. So out of order I mean outcome 1, 2 is the same as outcome 2, 1. Because what I do, I roll those two dice and I look at them and I see something on the table, but they both white with black dots on them. I could only read the outcome as 1, 2, even though if I know which die is which, I could say that die was 1, the other die was 2, or no, the first die was 2 and the second die was 1. But typically when you roll a pair of dice, you only read the outcome, right? So this 1, 2 happens in here, that's the pair 1, 2. In a grid like that, we usually write the row first. This is the row, so it's 1, 2, and the 2, 1, it's in here. But we won't be able to distinguish which one is 1, 2 and which one is 2, 1, because again, when we read the die, we only see two dice with the scores on them. We don't know which one was the first die. So similarly, this thing in here is 4, 5, and this is 4, 6, and this in here is say 6, 2. I won't write all of them. What is now the probability of a pair to be 1, 2 as a set? So that we say it's the values we observe is 1, 2. What is the probability of 1, 2? How many rolls of the die are going to produce exactly 1, 2? That's 2. Out of how many possible rolls do I have there? 36. Because the dice are uniform, each one of those rolls is equally likely. But there are 2 rolls that produce the set 1, 2. That's different than if you count, you have one red die and one blue die. Then you know which one's red and which one's blue, and then 1, 2, 1 red and 2 blue is different than 1 blue and 2 red. Those are different events. How about the probability of the pair 5, 5? How many of these rolls are 5, 5? 1. That's 1 over 36 because there's only one 5, 5 in here. There's only one way to get 5, 5. We assume again that each roll is equally likely. That's the probability of a uniform die. How about I define an event? I define the event, I want to take those squares here. This square, this is drawing like before. Instead of drawing it as a set of outcomes, I draw it as a grid. Every one of these squares is a possible outcome, right? I like these squares, these ones. This one, this one, this one, and this one. So what are these squares? This is 2, 6, this is 3, 5, this is 4, 4, right? This is 5, 3, this is 6, 2. So here's my event, E. E is the possible outcomes. 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2. Notice that in here I put 2, 6, and 6, 2. That way, when I say the probability to 2, 6, so if I'm to say what's the probability of E now? If 2, 6, and 2, 6 go to the same output, that is, see the scores 2 and 6, this probability is what now? 2 over 36, right? 3, 5, and 5, 3 go together, that's 2 over 36. And now 4, 4 is just 1 over 36. So the probability of this event is 5 divided by 36. Right? Because I have 5 outcomes if you look at pairs. If you don't look at pairs, if you cannot distinguish which one is 2 and which one is 6, then 2, 6, and 6, 2 are the same outcome. But in that case, its probability is 2 over 36. Because there's 2 ways to get it. Can I define this event more like set builder notation? This, how do I say this in a concise way? These are all pairs with a property. What's the property? Yes.
Sum equals 8.
Sum equal 8. So I could say this is what? This is the probability of the same event, just defined more concise. This is the probability of having a sum of die equal 8. Right? That's what it's saying. And what's the chance to get an 8 when you roll those 2 dice? Well, there's some possibilities to get an 8. So either you write it as a bunch of outcomes listed, enumerated, or as a concise, this is a set builder notation in effect. The probability of getting an 8 is 5 over 36. Okay? Another example. A bunch of deck of cards. Playing cards. Just because people apparently don't know the deck of cards, we know that from Wednesday. There are spades, hearts, diamonds, and clubs, right? Those are, how do we call those? Suits. And these are the ones that are 2 or 3 or 4, 5, 6, 7, 8, 9, 10. The next one is Jack, Queen, King, and Ace. Those are called what? Volleys or kinds. See, 3 of a kind, that means 3 kings. 2 in the same suit, that means 2 hearts. And what are how does those cards look like in case you really never seen a deck of playing cards? How is the heart 4 looking like? There is a little rectangle, right? With like 4 hearts on it. Maybe. Or it has, another deck of cards may have 4 hearts written on it somewhere. How is this card looking like? There's a dude, right? Looks like a king. He has a crown, and there's a diamond marked in the corner of the card. How about this ace of spades here? How does that look? Anybody saw that card? It's a big spade, right? In the middle, and some ace. So how many spades are there? How many spades cards are there?
13.
13 in each suit. And how many suits are there?
4.
If I want all aces, that means the ace cards on every suit, right? If I want all diamonds, that means all 13 diamonds. Okay? So suppose I have this deck of cards, and what is my sample space now? This is my sample space right here. The size of the sample space is what? How many cards I have? 52? Because my experiment here is draw 1 card. That's that. Or I could have another experiment. Actually, let's write it down a little bit so we have more space to write. I could have this experiment, but here's another one that says experiment. Draw 2 cards simultaneously. So I pick just 2 cards. In that case, what's my sample space? Remember sample space of outcomes. If I pick a card, how many possible outcomes are there? 52, right? Because I have 52 cards to pick from. But if I pick 2 cards, for example, I pick the 10 of hearts and the jack of spades. I could pick that as a pair. How many possible outcomes are there now? How many total different pairs? There you go. Good practice. She has the deck of cards with her. So that's 52. Choose 2 possibilities of choosing a pair of cards. Right? How many people follow me? Good. So now I ask these kind of questions. I have an event that is all cards. It's a set with pictures. Let's say pictures. Pictures actually a loaded name because in cards it means specifically something, or faces. Which ones are, let's say pictures, Jack, Queen, and Kings. Jack, Queen, and Kings have a dude or a woman on the card, right? So what is the probability of this event? If I pick a card, what's my chance to get a Jack, Queen, or King? It's a fraction, right? What's the denominator? 52, because there's 52 choices. And how many of those choices are Jack, Queens, or Kings? 12. Because there's 4 Jacks and 4 Queens and 4 Kings. Here's another experiment. Let's call this is E1. Here's another one. E2 is all cards between 2 and 10. What's the probability of E2? All cards that are 2 or 3 or 4 or 5 up to 10. How many of those are there? In each suit, how many things are from 2 to 10? 9. And how many suits are have? 4. So that is
36.
Divide by 52. Now, in probabilities exercises, as opposed to counting, often you are supposed to compute this value. Remember when counting, when we say you can leave it as factorials, multiply with 26 to the third. In here, the problem I specify, give me a digit value. Doesn't mean exact, it means with like 2, 3 decimals, the ones that matter. I'm a little lazy, I'm not gonna do this division, but typically in probabilities, you're gonna have to do this division and get the value. Actually, I have it written here, I think. I don't, there's 9 by 13 simplifications. I think I have a different one. How about in this case? So I'm going to define an event. Outcomes here are pairs of cards, not single cards, pairs of cards. I'm going to say pairs with pictures. How many of these cards have a picture in them? Pairs, right? So again, this one has a jack. So how do we do this? Probability of this E3 is the number of pairs with picture that is jack, queen, or king divided by total number of possibilities, 52 choose 2. So this is pretty much a counting problem, right? It's no different than a week ago when we said, if you are create pairs of cards, take 2 cards out of the deck. How many ways are there to create a pair with a picture in it? Right? How would you solve this problem if I give you, if I put in a meter? How many pairs of cards contain a picture? Seems like a decent problem for the meter. How do you solve it? How many pairs of cards contains a picture?
Well, you can first find the odds of just one of the numbers in the pair, or one of the cards in the pair being a face card, which would be Jack, Queen, or King. And unless you count ace as a face or not, right?
We said no ace, but some people count ace as a face. It's just a changing from 12 to 16.
So then this would be the 3 times 4, so 12 over 52 is the odds of just one of them. To get the odds of pair,
I think that's a way, a recipe for getting in trouble. But you can fix it. Somebody else.
You could just find all pairs that have no faces.
That's a cleaner way of doing it. How about I think of this as all the pairs
it's true.
minus the ones that have no pictures. How many pairs have no pictures? That's not done, right? I mean, I still have to do how many pairs have no pictures. So that is 52 choose 2, all pairs, minus pairs with no picture. No Jack, Queen, or King. Still divided by 52 choose 2. How many pairs have no picture? Somebody else. How many pairs in here can you create with no picture in them?
Is it 10 choose 2?
Why 10?
40 choose
Why 40?
2? Because there's 40, no, sorry, 36 choose 2.
Uh-huh.
Is that right?
Are they 32 choose pairs with no picture here? I have 36 cards. If she's looking at all these cards here, from all these ones up to the tens, she says there's 9 of those, another 9 in here, another 9 in here, another 9 in here. How many total? 36, right? 36 pictures, 36 cards with no picture. In how many ways can I choose 2 of them? 36 choose 2, right?
Wouldn't it be 40 choose 2 since
Because
we're
of-
saying aces?
We have to add the aces to it. You're right. 40 choose 2. That assuming this is something that needs to be clarified because there's conventionally when playing cards there's actually aces are counting as pictures for the purpose of the game. I know aces have actually no picture on them, but many games like poker or bridge consider ace one of these grand cards. So you have to be clearly specified what does it mean a face or a picture. If you take it literally, the cards with pictures are only jacks and queens and kings on them. But in this case, we don't include the aces, so aces are part of no pictures. That's 40 cards. There's 40 choose 2 ways to create pairs. So that's that minus that divided by 42. Yes?
We've done 12 choose 2 over 52 choose 2.
How much?
12 choose 2 for the faces.
If we do 12 choose 2, that is the pairs that contain 2 pictures. That's not what the problem is asking. It's asking you at least one
at
picture,
least one, okay.
right? With picture, that means at least one picture. So that's a different question. I want all the pairs that contain 2 pictures. Then indeed will be 12 cards. Choose 2. Do we all follow that? Good. So that's the card decks. Let's see, what else do we have? About earned problems. We have 15 red balls. Those are actually have IDs. So as opposed to balls into beans from last time, they are red 1, red 2, up to red 15. And I have 10 blue balls I did B1 up to B10. And I say, experiment, draw one ball. Random uniform. We will not say the word random anymore because everything is random now. Okay? When we say draw something, it means at random. It doesn't mean you pick the ball you like. That's not at random, right? If I always pick up Ryan here to clean the board, that's not at random. I always pick him. So from now on, there will be no word random because everything is at random. But we will still say uniform. What does uniform mean? Every ball is equally likely to get picked. Because sometimes things will not be uniform. Meaning some balls are more likely to get picked, right? What's the outcome space? What can I get if I pick a ball at random? Is this. The R1 all the way to R15, and then B1 all the way to B10, right? What's the size of this set? How many possible outcomes are there if I pick a ball? How many? 25, I think. There's 15 reds and 10 blues. I have an event here. What is the probability of picking exactly ball R1? So I say outcome is R1. Exactly the ball red one. What is that chance? Okay, but now I have an event that says any red. This event is actually all R1 to R15 because any red is good. What is the probability of this event? Picking a red, any red. What is the, so I could write this probability of red. This is informal. Red means any red. And what if I want the probability of blue? 10 over 25, right? How about a different space with those balls? I have now another experiment. Draw 3 balls at once. So what is my outcome? What can I get as an outcome when I pick 3 balls? I could get things like R1, R2, and R3. That's a possible outcome. I look at it as a set, not as an order, because I pick them at once, so they're out of order. That is, it's a set. What else can I get? I could get R1 and R2 and blue 1. I could get blue 2 and blue 5 and R9. What's the size of the set? How many possible sets of 3 I get here? If I pick 3 balls, how many different outcomes as a set are there? If I choose 3. Remember, those have IDs. R1, R2, blue 1 is not the same as R2, R3, and blue 5 because every ball has an ID. And I have an event here. All reds. That all the possibilities that red 1, R2, R3, R2, R3, R4, all the possibilities that are all red. How many of those choices? What's the probability of such event? Out of 25, choose 3 ways to get any 3 balls. How many of these ways are going to be all red? how many, comes down to a counting problem. It's saying if you create all the sets of reds, how many different sets of reds of size 3 are there?
15.
How much?
15
15 choose 3. Because there's 50 reds, there's 15 choose 3 ways to obtain a set of 3 reds. Another event, this is 2 reds, 1 blue. That corresponds to things like R1, R2, blue 1, so on and so forth, as sets. So those are out of order. Probability of this E2 will be out of all 25 choose 3 ways to pick 3 balls. How many of those ways are 2 reds and 1 blue? It's back to a counting problem, just like we had a week ago. I could tell you, I have all these balls. Count in how many ways can you pick a set of 2 reds and 1 blue. That count divided by the total number, it's going to be the probability. Somebody else. How many ways can I pick a set of 2 reds and 1 blue? 2 reds, 1 blue. Yes.
Choose one,
10 choose 1 for the blues times 15 choose 2 for the reds. Because those are independent choices, any choice of 2 reds with any choice of blue ball creates a set of unique set of 3, not counting anything twice. Remember the counting questions? Do I count all possibilities? Am I counting anything twice? Am I missing some, adding some extras? That works, any set of 2 times any set of 1. That's going to be the ways of doing 2 reds and 1 blue, divide by total number of sets of 3. There's another version of this setup, which is saying same balls, 10 blues. So there's the same set, but now the draw is draw 3 balls. This is a different experiment with replacement. Anybody knows what with replacement means? Yes.
When you take the ball out, you put an identical version of it.
Not an identical version, but what?
It back in.
We put it back in. With replacement means the draw is in order, is not at once. Not at once. It's one by one. And the ball draw is recorded, but then the ball goes back in. So this kind of experiments, definitely the outcome is what? Is a sequence. So this in here, the outcome was a set. I wrote it down this way, but the right notation is to put a set on it, because the way we look at those outcomes, we look at the set of balls that come out of the word, right? In here, we definitely look at the sequence. The outcome is something like R1, R2, blue 2. This is a sequence, which is not the same as R2, blue 2, R1. Although they are the same exact balls, they came out in a different order. And I have other things. Can I get R1, blue 2, and R1 again? I can. That's what with replacement means. I can repeat the same ball. Is this the same as R1, R1, blue 2? No. Different sequences. So now I have an experiment here, event. Is same like before, 2 reds, 1 blue. Any sequence that's 2 reds, 1 blue. What is the probability of this event? How many total sequences are there? If I take a ball, put it back in, take another ball, put it back in, take another ball, put it back in. Because I'm drawing 3 balls. So it's still 3 balls, but after each draw, I put the ball back in. How many total sequences of 3 balls out of 15 reds that are I did and 10 blues? We did this so many times. If I have, how many options I have for the first ball? When I draw the first ball, how many options are there? If I put that ball back in, how many options am I going to have the second time?
25.
And the third time? 25. Are this any option first with any option second, any option third creates a unique sequence? Yes or no? That's 25 to the third because there's these hats times pants times shirts, right? And everybody goes with everybody. Product rule. How many of those sequences will have exactly 2 reds and 1 blue? That's a counting problem. We look at the sequence. There's 3 things in a sequence. Think about choices, independent choices that we can make. If I am to have 2 reds and 1 blue, what can I choose first in this sequence? Choose the blue one, the position of the blue. So choose the position of the blue. X is the position of blue. How many ways can I do that? Choose the position, not the ball, but the position of it. 3 ways, right? Because there's 3 spots and there's 1 blue, and I'm choosing the position. So that's 3 for the position of the blue, or 3 choose 1 if you like, because that's what it is. Times what? That's the position of blue. Position for blue. Now for the blue ball, how many options are here? 10 options for the blue. That's the blue ball. And how about these other 2 spots that are the red balls? How many possibilities are there? How many possibilities for this spot? 15, because it's 15 red balls. How many possibilities for this spot? Because I still have all the balls in, right? Is any possibility works with any possibility gives me a unique sequence? Even if they come the same, R3 and R3? So how many options are there? That is all the sequences that contain 2 reds and 1 blue. Divide by all possible sequences. Let's see. How about coins? Actually, I want to go back to, but I don't know where that thing is. 2 dice. Do we still have 1 die somewhere on the board here? No. 1. So how about coins? Let's do coins in here. I have coins tosses. I have a coin. Has 2 faces, right? What are the faces of the coin? Heads or tail? Right? When I throw the coin in the air, I get either heads or tail. And I do n, let's say 10 tosses. If I throw the coin in the air, then I count the sequence that I see. For example, head, head, tail, tail, head, tail, head, tail, head, head. That's a possible sequence. For example. Now, suppose this coin is not uniform. The probability of seeing a head is, say, 40%. And that means the probability of seeing a tail, the P has to be a probability measure. It has to sum to 1, right? That's what we said. If there's two events, head or tail, if the chance of one is 40%, how much is the chance of the other one? 60%. 60% as in 6 divided by 10, right? Or as in 1.6 something. Now, what is the chance to see this exact sequence? Those are independent tosses. Right? So I take that coin, toss in the air, see what I get. Take the coin again, toss in the air, see what I get. What's the chance of getting this head? The first time. That's 40%, right? What's the chance of seeing this head? 40%. What's the chance of seeing this tail? 60%. And this is exactly what? This probability will be multiplied, right? What's the chance of seeing this times what's the chance of seeing that times what's the chance of seeing that? This is going to be exactly 4 to the 10 at how many heads I have, right? Because for each head I get 4 to the 10. Head, 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 head. That's 6 heads times the 6 to the 10 at 4 heads. Sorry, 4 tails. 1, 2, 3, 4. So this is the probability of head at how many heads times the probability of tail at how many tails. To see that exact sequence. Now, I could have another sequence, another outcome, that is head, 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 6 heads, and 4 tails. That's a different outcome. When I throw the coin, I may observe this outcome instead. 6 heads in a row and then 6 tails in a row. And I say the probability of this is the same. It's still P of heads and how many heads times P of tails and how many tails. Which is the same, because the number of heads is the same. They occur in different spots, but there's 6 heads, so that's still probability of heads at power 6 times probability of tail at power 4, because there's 4 tails and 4 heads, and this is the same, right? So those two sequences have the same exact probability. In fact, any sequence with 6 heads, no matter where the heads are, will have that exact probability of showing up. So now I want to introduce a concept. We have that example, and I'm going to put here back the example. The space was, you either get a 1 or 2 up to 6, right? And the probability of anything, say the 2, is 1/6, which is the same as the probability of 3, the same as the probability of 1, so on and so forth. That's a uniform die. The concept that I want to introduce, it's called random variable. What is a variable? So far, when we talk of variables, we say X, A, N, B. Remember number theory, we have those symbols. What do they mean? So what is a variable? Something with fixed value, sometime unknown. Right, in this problem in the midterm, if A is coprime with N, right? What is A? A variable. Do you know the value of it? No. Do you know the value of n? No. But it's a fixed value, right? That n doesn't change on you. You know my point? It says pick an a and an n that are co-prime. Those are variables. They have a fixed value. You just don't know which value is that. The changes on variables in computer science can happen, you know. In mathematics, it's fixed. In computer science, it's controlled, changed. You ever seen this in a program, I equal I plus 1? That's changing the value of a variable. But it's controlled by us. We decide when to change that value. This is very important. It's not changing it to where the program feels like that moment. We decide how to change it. Those are variables. What is a random variable? It's still a variable, but it doesn't have a fixed value. So in this case, the random variable, I'm going to call those x. X could be 1 or 2 up to 6. My outcome is a random variable, right? When I say roll the die, that outcome is random, right? I don't know what the outcome is going to be until I actually roll the die. So before rolling the die, the outcome is a random variable because I don't know its value. But after I roll the die, what is the outcome? Is it still a random variable? If I look at the die roll and see what happened, is it still random? Is it still an unknown value to me? If I look at it on the table? No. At that point, it's a fixed value. So before rolling the die, this is a random variable. For a random variable, no fixed value, but it can have an average. If it is numeric. I could average the die rolls because they are numerical values, right? Remember my first experiment, pick a student to clean the board? What is the outcome of that? When I say pick a student to clean the board, what's the outcome of that experiment? Yes, a student. Is that a numerical value? Can I average them to say what's the average? No. But how about the die rolls? Can I average the die rolls? I can. So here's how that average goes. Average is the same as mean, is the same as expected value. It's called E of x. It's the sum over all possible values, the value times the probability of that value. So in the case of a die, what are the possible values? It's 1 times the probability of 1 plus 2 times the probability of 2 times 6 times the probability of 6. Right? These are the possible outcomes, and those are the probabilities of the outcomes. Now, if the die is fair, what does it mean, fair die? All probabilities are, so that would be 1/6 divided 1 plus 2 plus 3 plus 6. That would be about 3.5. The average value for uniform die is 3.5. Because you take those. Now, of course, if the die is not uniform, if 6 is more likely, the average will increase. Because the probability of 6 is not going to be 1/6 anymore. It's going to be a bigger probability, right? Here, I can define a different random variable. Number of heads. Remember my experiment? I toss this coin in the air 10 times. Can I count the number of heads in each toss? Is that a random variable? I mean, once I do the 10 tosses, it's not random anymore. I know exactly how many heads I have. But before, ahead of time, can I tell how many heads I'm going to have? No. That's a random variable. Is it numerical? The number of heads, is it a number?
Yes.
It's a numerical. What is the expected value of x, or the mean, or the average? Is the sum over all possible values. How many heads can I get in 10 tosses? What's the minimum?
Zero.
Minimum is 0. So it's from 0 to 10, I can get 10 possible outcomes here. Remember, the outcome is the number of heads, not the sequence. Now, is the value times the probability of that value. So to compute this sum, we're going to need to know what's the chance of getting 10 heads. What's the chance of getting 9 heads, 8 heads, 4 heads? Because this sum goes for all the heads. So for numerical, random variables don't have to be numerical. They could be a student. It could be a pair of cards. But if they're numerical, they have an average. All right. We'll see you guys on Tuesday. The attendance sheet, please. We have it. Can you press the pause button? There's a red button on the right side.
Oh.